Welcome to Kvaser's presentation of the future CAN Excel standard. Let me introduce myself. Lars-Göran Fredriksson, many knows me as Helgi. I'm working as a field application engineer here at Kvaser. Before we start, I want to mention some things. This session will be recorded. It can be accessed later via our CAN Excel homepage. You can find the link at the bottom of the presentation, the red bar. There you find the link to our CAN Excel homepage. Now, Kent Lennartson, with some help from me, will present some interesting details regarding CAN Excel. We have pre-recorded the presentation. Please add questions or comments in the chat, and we will try to answer your questions after the presentation. You can also mail your questions directly to us at support@kvaser.com. Let the show begin.
This is a presentation of CAN Excel. So CAN Excel is new CAN technology, so it's based for classical CAN or CAN FD, and this will extend into the future. And CAN Excel also comes with new CAN driver that makes it possible to increase the bitrate maybe up to 30 megabit per second. We start here with CAN Excel is to compare the different protocols CAN FD and CAN Excel. And what you see here in the bottom is the three different frames, classical CAN, CAN FD and CAN Excel. And as you can see here, the CAN Excel frame includes a lot more than we have in CAN FD and classical CAN. But we will see that all those parts have some function that are good for us in the future. When you start to communicate, they all send concurrently. You may start a frame. You send the 11 arbitration bits to find the priority, and the one with the lowest number here in this part win the arbitration. And then you go to bit remote request, which is not supported by CAN Excel or CAN FD, and ID a bit here. So those first 13 bits are identical. So the next step we go into the versions. So the next bit after those 13 bits is the reserved classical CAN. So this bit here in classical CAN is dominant to indicate that this is a classical frame. So when we come to CAN FD, they send this bit as recessive. And when the classical CAN frame sees these recessive bits, it knows that there's a new version of the bits, so it wouldn't understand the bits that follow. So, and the classical CAN controller doesn't know what to do, so the only thing it can do is to send an error frame.
So they will accept each other?
CAN FD will send and receive classical CAN frame as CAN FD frames. But classical CAN, if you send a CAN FD frame, it will just get confused. And the only thing you can solve the confusion with this is to send an error frame. So when FD has also reserved FD bit, so when it comes to new protocol, instead of this dominant bit, you will see a recessive bit. And again, CAN FD doesn't know anything about CAN Excel. So the only thing that CAN FD can do is now, as classical, send an error frame. But in CAN FD, there are also a function where you tell the CAN FD controller that if you see this recessive bit, ignore all that bits here along and wait till you see the end of frame, and then you join the communication again. CAN Excel have again a reserved bit, and it will do the same. If you have a future version sending this bit recessive, it will just ignore everything up to the end of frame in the future versions. So here you have a table where you can see the different CAN controllers. So you send classical CAN frames, all three can send and receive those CAN framers, the classical CAN. When you come to CAN FD, the classical CAN will send an error frame, as well as it can do for CAN Excel and future version. But CAN FD will, when you see a CAN Excel frame, will just ignore them, as well as it will ignore future versions and join the communication looking for the end of frame. And CanExel is doing the cell. It works perfectly well. If your future version, you just ignore it. The next difference here is the bitrate switch, which is not supported by classical CAN, so you don't have CAN. But CANFD do bitrate switch and CanExel do a bitrate switch. CanFD have this bit here, knowing synchronization. The problem is that the bitrate switch is done in the bitrate switch bit at the sample point, and there is some time here. So during this time you can have a clock off variation offset in the phase, which make an uncertainty where the data bit starts. With an error status indicator is the first bit. In CanExel, you do the same, but here is a second recessive to dominant edge that synchronize the data bits sample point. So even if those bits are extremely small, the sample point will come exactly in the correct spot relative to this edge.
So on CanExel, it always will happen here.
The bitrate switch is actually here, but it will resynchronize the sample point there.
Okay.
And here it doesn't matter. This bit here has another function as well, that arbitration to data high bit is because it's here where the CanExel SIG drivers switch the mode from dominant recessive, which you need for the arbitration, to a push-pull mode. Which is much more efficient when you want to go to the higher bit rates.
So that means we are getting rid of the problem with CanFD networks where by mistake have different sample points between the nodes, because they will change on different time.
Yes, that's next slide actually.
Oh.
So this here is about the phase offset you get due to the clock variation. If you look here, we have a second problem that adds to the first problem, is that if different nodes have in bus have the sample point at different location, that will add an additional phase offset to the start of the data bits. But again, because of this edge here, which will synchronize the data bit sample point correctly, you don't have that problem anymore.
So now we are somewhere here.
Yes.
Yes, and that means now we have changed the speed to high speed and the push-pull.
Yep.
So now we are start sending all the data bytes.
No, we still have some more. The first byte comes here, so we have to go through this section first before we reach the real data.
Okay.
So the next part we will jump into is the data length code. So we will come back here to the other section here in the communication. So classical CAN and CanFD had 4 bits for the data length code. Classical CAN used 0 to 8 byte, and the number 9 to 15 will still result in 8 byte. Where in CanFD, the number, DLC number 9 to 15 will means 12, 16 up to 64 bytes. So you can, in CanFD, send groups of up to 64 bytes. In CanExel, it switched to an 11-bit number from 0 to 2048, 47. Plus 1 is, so the actual number of bytes is 1 to 2048. We have a problem with the CRC, because to have a theoretically valid CRC, you need to know exactly how many bits you have put into your CRC. So a problem here, if you have a data length code, is that the length of the number of bits depends on how many bytes you have in it. So you have to know that this number is correct. So to protect this number, we have a stuffed bit counter and a CRC here for this first part to make sure that we don't have any error in the DLC. And when we know the number of byte, we know exactly how many bits we have put into the CRC here for the frame CRC. And by knowing this, we know that we can guarantee mathematically the Hamming distance 6 of CanExel. Then you see 6 more bytes here And
but we are still outside of the 2048 bytes.
Correct.
Yes.
We have defined in the protocol here for CanXL 6 bytes for layer 3 functions. Reserve them, and if you don't need any higher layer protocols, you can actually use this as data bytes, or because they actually just data, but they are predefined for certain functions in the higher layer protocols.
And there are some standards for this?
Yes, we look there are 3 parts. We have the service data unit type, which describes what you would expect in the rest of the frame. And there is a standard in CAN automation 611-1, which gives some description how it's intended to be interpreted. But it's actually a switch here. So the idea here is like you have an Ethernet that where you also have a type descriptor. That tells, so you can say this is a J1939 frame, and then you know that the information here is contain J1939 information, or it's CAN open, and then you know that this is a CAN open information here, or it is a Ethernet frame, then you know there is an Ethernet frame. So that's the philosophy of this byte here. And the bit here is just a fast bit, just 1 bit can switch between 2 protocols, like CAN open and J1939. This virtual CAN network ID is something also taken from Ethernet, where you have the vertical local area network. And actually is only described how it's going to be used for Ethernet tunneling in this document 611-1. So actually you can invent a new function in a higher layer protocol, or you follow this CAN automation standard for it. The acceptance filter is 32 bits, and this has something that more related to classical CAN and CAN-FT, because in classical CAN and CAN-FT we typically has a filter, mask and masking on those CAN ID bits to select certain information, so you don't need to get an interrupt for every CAN frame. For instance, in J1939, you have a destination address here in the CAN ID, but now you will, instead of using up here, you will move the destination address in here, and then you can have a mask and a filter here, so you only have to receive the frames with the destination address that match your node address.
It looks like that this will take more space to do that, but right now we are in the high-speed mode, so we will save time.
Correct. And this information, if you have a J1939 system, either you have to put it in a 29-bit identifier or put it somewhere else. And so instead of 29 bits identifier, which is typically what you use in J1939, you have only 11 bits here. But again, you have to put the information somewhere, and then you put it here. So even today you have this information. It's just that you relocated the information in the CanXL frame. And then we come to the real byte of data.
Now finally we are there.
Yes.
My single byte or my selected number of bytes.
You mean the DLC here,
yes.
Which go from 0 to 2047.
Yeah.
So if you take this number, it doesn't tell how many bytes there is. You actually have to add 1 to get the number of bytes there. And that's because they didn't want to stop at 2047. They wanted to go to 2048 because that's more nicer in a binary system.
Yes, I agree.
And it's linear again, so you don't have, still CAN was linear, 0 to 8, but limited to 8 byte. CAN-FT was 0 to 8 linear in the beginning, but then you have these 16, 20, 24, 32 to 64. But in CAN-XL, you can match your CAN frame to the actual data format from 1 to 2048. And a really big reason that we move from up to 2048 is when you do flashing, you would like to use TCP/IP or some other good protocols. And to do that, we need to we don't want to fragmentate the frame, Ethernet frame. So we would like to put the whole frame, so we know that when you get the frame, it's correct due to the CRC. And when you put the whole frame in there, you know it's there and it's correct. And that makes life much easier for the software. So that's why we have those 2048 bytes. And the end is just the CRC, and as you can see here, for the 8-byte we need 15 bits for the CRC. For 64-byte we need 27 bits, and for 2048 bytes we actually only need 32 bits to get the same Hamming distance of protection to the data frame.
But if I discover that something is wrong during this phase here, then I don't interrupt anymore.
No. If when you go here into the push-pull mode with the new CAN-XL SIG drivers, they would not. You need the dominant and recessive levels in the communication to have the means to send an arrow frame, because our arrow frame has to win over any bits, and that you can only do if you have dominant recessive bits. When you do the data phase here, the CAN-XL SIG drivers is a push-pull mode, and that means that dominant and recessive mixed with there will be undefined level, and you can get anything.
So I must sort of save this error in the memory and doing something over here.
Correct. The same as previously in classical CAN and CAN-FT. If you detect a CRC error, you will not allow to send a error frame here. You have to wait to go to the end of frame, and that will be true in the future as well. If you see errors here, you have to wait until you come to the end of frame and tell that there is a problem.
Yeah, but how do we switch to normal speed again?
Okay, we see here. So here after the CRC, before we have only a CRC delimiter, and then we switch into the AC part. But here we have to do some more work. So we have one edge. This here, even if they look the same, this is the data bits, the 4 first here. And here you have an edge which synchronize all receivers to this edge. And then we have the data to arbitration bit here, where the CAN driver, the CAN controller, the CAN-XL CAN controller will stop sending PWM, which is indicated for the driver that we send in push-pull mode. And then the CAN driver will switch the output driving stage and the input driving stage to match the old traditional dominant recessive level.
So we change the behavior and also the speed at the same time.
Correct. And then we have a second end here to synchronize everything here before we go to the ACT section, which is a critical part because it's arbitration again. So it's only one bit, and there is one sender, one passive. The sender is sending this ACT bit here. We'll come to the next section. We'll move to that next scene better here. So this ACT bit here, again, from here to the end, all 3 protocols is identical. And in all protocols, this ACT bit here will be by the sender be sent recessive, and all the receiver will send this as dominant to indicate for the sender that this looks okay. And if it's not okay, they will send a recessive, and after ACT delimiter, they will send an error frame. So this is both a negative and positive acknowledgement to the information that the receiver has a receiver. And this is a very important part in CAN, because this behavior secures that every receiver on the CAN bus gets exactly the same information. It can't be that one receives it and one doesn't. Either everybody have received it without any errors, or there will be an error frame and it has to be retransmitted. And that's if different nodes synchronized need the same data, it is protected by the CAN protocol itself.
During this phase here, we need push-pull mode, we need much higher bandwidth, etc.
No, you don't need it. The push-pull just makes the signal, the energy switching from 0 to 1 bits behaving more nicely. So it has nothing to do really to that. It's just to make the signal more nicer.
But we do need new transceivers.
Correct. We will come to that, I think, in the next few slides.
Oh.
Yes. I think we get it here.
Yeah.
So CanXL support all, as well as CanXL's accept classical CAN frame and CanFT frame. You can use legacy CAN drivers. So CanXL, first of all, yes, it supports this new CanXL SIG drivers that runs in a push-pull mode. And due to the push-pull mode, you will very symmetrical bits, which make it possible to run up to, I would say, up to 30 megabits. We've proven in a test in Detroit that it was no problem to run a pretty long bus with drop lines up to 20 megabits. And I think there was a lot of margin to go beyond that, but it was never tested. If you go to legacy SIG drivers, they have some electronics to make them the ringing less prone to ringing, and I think if you use them, you can maybe go up to 10 megabit per second. And if you use the traditional high-speed drivers, 4 megabits is what you can expect from that.
But using a SIG driver on 500 kilobit, that will give you much better EMC.
Correct. As well as I would suggest everybody to go to those legacy SIG drivers that are intended for CanFT, but actually they've improved your EMI a lot if you use it even for the classical CAN driver controllers. So I would suggest if you can afford, move to the SIG drivers. But the CanXL SIG drivers, they need a CanXL controller, so they will work with CanFT and classical CAN, but you don't get this push-pull improvement. So you cannot go to, in that sense, both of those are the same. So you need CanXL to utilize the higher bitrate.
Yeah, but the CanXL SIG drivers will be backward compatible with the sort of legacy CAN drivers.
Yes, but you don't get the full performance. And again, it doesn't help to have the world's greatest CAN driver or driver whatever if your cable doesn't allow the energy to come through undisturbed. So to get to the higher bit rates, you need to be carefully watching for the impedance variation. And the impedance variation depends on the bit rate or the slow rate. And impedance variation really is distorted by long drop lines in clusters, like a star, and to some degree of the EMC filter in the nodes itself, which can cause storage of energy. And this is a short few slides here about CanXL compared to Ethernet or other solutions available on the market. And the good thing here with classical CAN, as we said here, it can use the same drivers, it can use the same network as classical CanFT, and you can use the same development strategies. The prioritization, the real-time performance is the same, even though if you make really long frames that may delay some signals. So there is a lot of legacy and history you can bring in with the CanXL, and from there you can take the next step into the future, better CAN drivers, better networks to increase the performance even beyond that. So again, CanXL compared to Ethernet is good because there's a lot of software, but there is a relatively high overhead, and you have less here. And again, with CanXL, you get the real-time performance for free, more or less, by the priority and the limited length of the CAN frames. So when you go to CanXL compared to Ethernet, the big competitor is 10 base T1S, which has multiple nodes on the drop lines, but it's 10 megabit. Where in CanXL you can select it from 125 kilobits up to 20 megabits. So it means that if you have a cable already, you can test how much you can get out of the layout. And if you improve the layout, you can improve also the bit rate, and actually you can go beyond those 10 megabits and reach those 20, or maybe in some carefully designed cable layout reach even 30 megabit per second.
So you must spend time of the layout of your network.
Yes, again, it's all about impedance, and if you do something in layout that give you bad impedance, that will kick back and prevent you from reaching higher bit rates.
If I want to start using CanXL, where is Kvaser? What kind of equipment do we have for the moment, and what do we plan to release in the near future?
Well, let's step to this, CanXL and Kvaser. So yes, we have a CanXL IP block that we today have placed in our M2 module. So we actually have 4 CanXL controller there. We even have, by good connection with NXP, we have those CanXL SIG drivers with the PWM functionality, so we can reach those 20 to 30 megabits. We have run this in Detroit at the Plugfest without problem with communication. We could see there are some problem with error handling. That's not 100% identical to what Bosch is doing. So we really need CNS in Wolfenbüttel to get their verification hardware up and running, so we can go there and find those small obstacles.
And CNS is?
It's a company in Wolfenbüttel who actually is the main source of testing all ASICs and CanXL controller and CAN controller today, yes. And we are working, we have a CanLib XL now, so we can send and receive CanXL frames. But again, there will be some work before we expect in about 1 year that the software department has implemented this at CanLib. It's a little bit critical because we need a good system that can allow us to receive 2048 byte and suddenly receive 10 short frames with 0 byte with higher priority. So we don't want those long frames to block low priority frames. So we have to find a nice way to modulate that so we still have a good real-time performance of our CanLib. The problem again, those CanXL drivers, I get them directly from NXP. Which means that to provide you with those, we need an NDA both from Kvaser and from NXP. It will only be a few customers where we can provide the CanXL technology for at least for this year. Maybe in the beginning of next year we can more easily provide the technology to some interested customer. But it will be on an NDA. It's hard for us because it's not working perfectly well. So if we give something away, we need a good customer relation, which means that we need an NDA, both from Kvaser to make sure that the customer understand that this is a prototype or beta version that, yes, seems to work, but we know that we will change both the CanLib and the hardware before we go to the final products. So we will need an NDA.
The standard is not set yet. You're still waiting for that. Will we release anything before that?
Yes, I'm sure that as soon as we have something that we from CNS here can trust, we will. But again, CanLib will take another year, so there will be some kind of limitation for the customer for the time being until we have a real product that you can buy off the shelf. So it is. That's the problem today to get it validated correctly. So I think this is the last slide here. So we go to the next section, and that's questions. And now we will see if I think there's possibility to get some questions and answer after this session.
Thank you very much for listening. Yes, now I hope we have plenty of questions and comments, and we will try to answer some of them now. One question that I got directly is, will you make the webinar available later? Yes, it will be available on our homepage, and we will also send out information to all of you who have registered. So yes, you will be able to download it. And yeah, well, here we have one question, and this is any of the Kvaser interface be upgraded to support CAN XL?
Not all. The CanXL IP is a little bit bigger, and so it has to be tested device by device. Some of them, I'm sure it will be possible, but which and when is another question.
Okay. I have a question here regarding J1939. Where is J1939 on transport over CAN XL?
Well, it's something that has to be defined by the J1939 group, and I haven't seen a new standard, but there would need to be like a J19. I think there is a transport protocol -22 in J1939, and possibly that support CanFD, and they will have to write something similar for CanXL. I think it's a good idea to rewrite it because by the longer frame, you don't need those fragmentation protocols that you have defined in -21 and -22, because now most of the frames you fragment there. You can in CanXL, if you rewrite that into a new J1939 standard, you can probably send a lot of the frames as one piece of data. Especially when you're flashing, if you do the real-time systems, sometimes it's a good idea to keep the fragmentation, because that means that between each fragmented frame, high priority messages can come through, and that's for real-time communication. But for flashing, normally the truck is stopped, and then you can use the longer frames.
Okay. Have another question here that would CAN XL would be TDMA similar to 10-base T1s?
Well, CAN always is based on priority. So and that's one of the big features with CAN, that if you want to send something, you have a certain priority, and you just send it, and then the one with the highest priority wins the communication without crashing the communication and causing an error. And as you know, there is a TT-CAN, which is a time multiplexed protocol on top of CAN. And again, on CAN, you can put any restriction. You can make it token ring or token bus or time slotted, or any extra rules can be put on top of it. So I'm not sure if that answered the questions. There is in T1S, they use this PCLA, I think it's called, and there's a new one called DPCLA, which actually a combination of time slots and a round robin thing. But then you need a network master that make up the ordering of the nodes in the system. I hope that's the answer of the question. I'm not 100% sure that this was the information he asking for. Maybe can put another question up there.
Going back to one thing you already answered on, and that is now it disappeared for me, about the push-pull driver. We don't have it on our interfaces yet.
No. So if you're gonna support, so if we again, if we talk the product, if you already had a Kvaser product, and we will support CanXL for that product, it will not have the possibility to run at the push-pull mode. It can only run on the. As a matter of fact, I don't think even we have SICK drivers even. So we have legacy CAN drivers. So typically you're limited to 4 megabit. Even if you upgrade with CanXL, you will not get more than 4 or 5 megabit per second. So then you have to wait until we get the CAN SICK drivers, and then you maybe get to 8, 10 megabit. But to go to the CanXL, you need to replace also the CAN drivers. But I think if we make a new product with CanXL, it will come with the CanXL SIG driver, so we will support the full 30 megabit with those hardwares. When if we make it possible to upgrade CanFD with CanXL, you will have this limitation of the bitrate because otherwise you have to resoldering the CAN drivers as well.
Yeah. Here is a little bit complicated question. I will send it out. Will CanXL be more targeted to carry CanFD frames intermixed with Ethernet data, example J193922 and camera video?
No, not really. First of all, if I'm in IEEE 822.3, where we are working on image sensor camera interface with Ethernet, and then we talk about 10 gigabit per second from the camera. And CanXL with 10 gigabit per second, we will not see. So when it comes to camera video, I would see CanXL is not there. Today they mostly use MIPI with LVDS, and now they try to move over to Ethernet. And I think for those application, you have to stay. It's more suitable to use Ethernet or in 10 gigabit than try to squeeze CanXL to 10 gigabit. So CAN is a real-time protocol for controlling smaller control systems and not for streaming video information or voice.
About limitation in CanXL. Is there any limitation in CanXL when it comes to sample point settings?
Not really, as CAN and CanFD, CanXL all do arbitration. So you need a propagation segment in the bit for arbitration to handle the delay over the communication to have a proper prioritization in CAN-ID, but which force your sample point to put it to the rear of the arbitration bits. And when it comes to data bit, the only thing is you want to protect the sample point, and in that case, the best location is in the center of the bit. Especially if you push pull, and if it's dominant recessive, you normally want to put the sample point a little bit behind the center. But other than that, you can put the sample point at any location. But again, you have to make sure that the sample point comply to the physical rules of the signaling. But not when it comes to bitrate switch, it doesn't matter where the sample point is located.
One question that asked from many here: where do I find more information regarding CanXL? And that I think I can answer directly because I will add it in the chat here. If I just manage to do that, yeah. I send out a link there to CIA where you can find a lot of information regarding CanXL.
And I think we have some information on our homepage as well.
Yes, of course we do. One question that I actually really want to know a little bit more about, I'm sending it out right now. It will be public. What is the fate for CanFD in the future? Do we still need CanFD, or should we go straight to CanXL from CAN? Do you have your crystal ball?
I would say if you haven't started to produce any CanFD products and your plan is to do a CanFD product, you should consider to wait for CanXL if you can. So I would say that the same in the CanOpen world, the CanFD has not been a huge hit. and it is because you have so many products out there with classical CAN, so it's very hard to utilize the CANFD functionality because you need to replace all nodes with CANFD before you can run CANFD in the classical CAN network. And so can XL give you so much more? Both that the bitrate switch makes it possible to go beyond the 8 megabit. You can go 10, 20, maybe even 30 megabit. The long frames, to me, isn't a good idea to have the long frames for real-time function. But when you do the flashing, they speed up the flashing time a lot if you can send long frames, especially if the new microcontrollers where you have maybe 100 megabytes of flash memory, whereas sending this in small 8-byte chunk or even 64-byte chunk is quite time consuming. So sometimes you're stuck with the history, and which makes it hard to switch. But if you have the freedom to switch, I would suggest to wait for the CAN XL and go if you can wait.
Okay, here comes a question. It's too difficult for me. There was a discussion on the introduction of MICI, Media Independent CAN Interface. Is it only for CAN XL and future CAN, or would it apply to CAN 2.0 and CAN FD?
I'm not sure if there has been such standard. I would say in this case it's even worse because this new PVM standard that has been added to CAN XL is the completely opposite to that media independent interface, because now we have a CAN XL dependent CAN interface in contradiction to this standard. So I'm not sure. I have to come back to that question, but to me, the simple thing is no. And I saw another question: can you mix drivers? Yes, you can mix drivers, all three of them on the same network. But as soon as you use the push-pull mode, this is not supported by classical CAN or CAN FD, so they will crash if you start it. First of all, they cannot run the CAN driver in PVM mode, so they don't know how to do them. Get them into the push-pull mode, so they will never turn the driver into push-pull mode, even if the driver support push-pull mode. So they will fail in any cases. So if you go to the push-pull mode, that will only be supported by CAN XL controllers.
Okay, I have a question for you here. Can you elaborate again the PVM capabilities of CAN XL? Where in the protocol is PVM implemented?
So this is just an extra function so when a protocol comes to the certain bit, you can program the CAN XL controller to switch instead of you sending just ones and zeros, dominant and recessive bits into the CAN driver. You start to send a pulse PVM mode. And when the CAN driver detects these PVM signals from the CAN XL controller, it will switch into the push-pull mode and stay in the push-pull mode as long as you have the PVM signal. And when the PVM signals disappear, they will switch the CAN driver back into classical dominant to recessive mode and send with arbitration. I hope that explains it. Otherwise, the person has to put another question about it.
Okay. Meanwhile, I'm publishing here. Do you have any information how big the industry's interest in CAN XL?
Well, there is you can definitely see in automotive industry that there are some players that seems to stay with the CAN technology, and there are other players who seems to leave CAN completely, and some players that will have both of them in combination still. But again, even those players that go 100% Ethernet, they will stick with CAN because you always have some nodes like a window controller or seat controller, and if that is CAN or classical CAN, you will not throw them out if they are good enough. That's true.
At the same time there, maybe you already answered it, but I got a question here. What is the target market for CAN XL? What I heard, many people believe the CAN XL is only for backbone networks.
No, I don't think so. There is two reasons to go to CAN XL really. One is you want to increase the bit rate, which is more easier when you have this push-pull mode, which can and this better switching compared to CAN-FT. So one reason is, and it's flexible in that way. You can select from 1 to 2048 bytes. So it's you don't have this fragmentation in blocks that you have in CAN-FT. So you can make it very easy for the software engineer to match what you send on the bus to what you want to send. And again, real time, it's very easy to make a real time system with CAN due to the prioritization that is very efficient way and simple way to get real time performance. And at the same time, so in a real time communication, you need to use short CAN frames to keep the response times down. But during flashing, at the same time with CAN XL, you can make very long frames and make the flashing very efficient. But I don't think you will, under normal control systems, you will not use the long frames. Then you will use the short frames and use CAN XL just because it's you can make the frame shorter by increasing the bit rate a lot.
Yeah. See, we have got a lot of questions here. I think we have answered many of them, and but we still have someone. Here is one I like very much. What is Kvaser's role in developing CAN XL? I like that question.
Yeah, well, we are into CAN XL, and we are joining in Detroit, and actually, I think most of the people in Detroit use Bosch CAN FTP. I think it was only Kvaser and Vector and Bosch with the IP. So there is more IP blocks, but in Detroit there was only 3 of us. So we are developing, and we are involved in both in CAN automation, and I'm a member of ISO. So in the standard writing the new ISO 11898-1, which will now include CAN XL, and hopefully it will be, we are on stage 40, and you need to go to, there is 10 steps in ISO organization. But now I think we mostly look into what you call editorial problems. So probably it will be subject for voting in ISO in the beginning of next year. And I'm also involved in IEEE 802.3, where I in T1S, T1L, the DGDA, and the new standard for 10 gigabit Ethernet for video signals from the cameras.
Okay, yeah, we can say that Kvaser is one of the big players.
Yes.
Yeah, okay. One question here, that's too difficult for me. Is it possible to define unique MAC similar, similar to Ethernet for CAN XL?
Well, this is a higher layer problem, really. In Ethernet, they put the MAC in the Ethernet layer 2 protocol, but actually it is a layer 3 or even layer 4 problem to do the addressing. But again, you have this virtual CAN ID, and that is something that could be used as a MAC address to have a layer 2 switching of the frames, even if you have a switch or a rotor. But this is not really the standard CIA 611-1 has not described this. So no, there is at the moment somebody has to do that work. There, I haven't seen anybody doing that work. Except if you look at in J1939, they actually has a node address which ends up as a source and destination address in the CAN ID. So there you can say that there is an 8-bit MAC address, which in many cases, in very few cases, you have more than 256 nodes in the CAN network, where the MAC is a lot addressing. So the question is how big the MAC will be in this case, because if you look at the CAN bus, 28 byte, 1 byte is enough. But if of course, if you want to address every car in the world, then you need a longer identification. But as far as I know, there is no actually work on implementing MAC technology in the CAN-XL layer 2 controllers.
Here comes another question. What is the build of material cost for using CAN XL compared to CAN FD and classical CAN when it comes to ECU development? I believe it's very much connected to the transceiver that needs to be changed, etc.
I think that's true. Of course, the CAN XL runs on legacy CAN drivers. So if you're happy with 1 megabit per second, there's no cost at all to use CAN XL. But again, if you go to the CAN XL SIG drivers, I am sure the producer of them will try to squeeze some. They will be more complex, so they will cost more. But I doubt it. Maybe it's the double cost. No, I wouldn't expect more than that. And still, the CAN XL SIG drive is much more simpler compared to an Ethernet 10 base T1S controller or T1L driver. So that's I'm sure. If you go to the CAN XL controller, they are just slightly bigger than the CAN FD. It's not very much, but that's a but. If you're gonna receive a lot of 2 kilobyte frames, you need a huge buffer size in the CAN XL controller. So either you need some DMA or something that can get the data out of the CAN controller, or you need a huge double port RAM in the CAN XL controller, and that will be the major increase in the cost. But again, I think if you use a CAN XL controller just for flashing, the long frame for the flashing, you don't need a very huge CAN XL frame either. So then you can stick with the smaller buffers for the real time and use some other technology for the larger 2K frames. So is there any more? I think that's
Yes. We have one more here, and I'm trying to publish it, and it's about the future. How and when do you see CAN XL coming into the HD truck industry? Will it drive changes to the internal architecture of the vehicles? I would say that's very difficult to answer, I think.
Yeah, I don't think so. If you look at real-time control, classical CAN many times, 8 byte it's very little, but I can see a reason in the real-time system to go beyond 8 byte, and that one reason to go there is to go to CAN XL, and the main reason to go to CAN XL is because you can increase the bit rate, and If you increase the bitrate, you make the CAN frame shorter, which means that they take up less time on the CAN communication, which means that you reduce the latency in the communication just by making the CAN XL frame shorter in time. But again, the real long frames, it's to me, it's the main target is for flashing, which makes and if you have like 40 ECUs with a couple of megabyte per ECU, that can reduce the flashing time a lot if you can make the longer frames. But again, I don't know enough to like understand how they do the HD trucks today and how that will affect by the CAN XL. Then I need more information to answer better than I already had done.
Okay, I think we have answered all the questions. Please, if I have missed any questions, please resend them again. Or if you have new questions here.
There is one question there about the transport protocol
Yeah.
and fragmentation. One actually, to me, they are the same thing. Transport protocol or is just fragmentation. They are the same to me. And if I misunderstood something, somebody have to explain for me what's the different, if there is a different fragmentation or transport protocol. So yes, of course, if you send more than 2048, and the good thing with the Ethernet tunneling is because you can send the Ethernet frame. It means that CAN XL will transport the Ethernet frame, which typically based on TCP/IP. So if your ECU has a TCP/IP endpoint, you can send the TCP/IP directly down to the module, and you know that the CAN XL or the CAN protocol doesn't do any harm because the Ethernet frame is protected by a CRC in the CAN XL protocol, which makes that the CAN XL communication is completely transparent to the TCP/IP frames from the central computer and the ECU receiving the TCP/IP file and the file over the TCP/IP communication. So that's really, you can do it 100 different ways, but again, TCP/IP is standard and it's available in most computers. And if you can afford to use the more complex software, that's a very quick and way to get a working solution that you know will work.
Okay, I think that was all questions, and I certainly hope we haven't missed anyone, but we will double check that, and if so, we will add it to our homepage. Okay, if you haven't found it, our CAN XL homepage, you will find it, of course, on our homepage, of course. But you have this red bar. Visit our CAN XL page there, and you will find the link to our homepage. And I will thank you all for listening. Me and Kent and all at Kvaser, we thank you for all the questions and comments, and we hope we will meet you soon. As I said in the beginning, and it has been repeated many times, you will be able to access this webinar together with questions later on our homepage or on our CAN XL site in a few days. And we will also send out a message to all of you who have registered. Thank you very much, and goodbye.
Goodbye.